Let's suppose that we have this function here, y equals 2x squared plus 1. Now notice, y is explicitly defined in terms of x. In other words, you've just got y equals. And if you want to get the derivative, that's no problem. You know, dy dx, this is a simple one for us to differentiate. That's just going to be 4x. No worries. Now, let me mess with this a minute. Let me multiply through by, let's say 3. So now I have 3y equals 6x squared plus 3. And let me bring this 6x squared over. So now I have this function. Now, this is the same function, and you can show that if you just want to solve for y. You know, you could solve for y, and you would get this exact function back. So, dy dx is the same. Now, here's the thing. This is not, we don't have a situation here where y is explicitly in terms of x. Y is defined implicitly. So we would like a way to still find dy dx without having to actually solve for y. And you might say, well, I'll just solve for y and find dy dx. But there's a different way, maybe a little more, well, a quicker way, and sometimes we will have an expression where we can't solve for y. So this technique is very useful. So what I want to do is I want to go through here and recognize that x squared is the independent variable and y is the dependent variable. So in other words, y is dependent upon x up here. I mean, and when it's in this form, I don't know what y equals. I do know it's something in terms of x. So here's what I can do. I can go through here and differentiate. But whenever I come to the y, I'm just going to put y prime, unless I just understand that this is dy dx. And I'm just going to use y prime here. Okay? Minus, now I differentiate the x part, and I get 12x. And then I differentiate the 3, and I get 0. Notice, I just went through there and differentiated everything I could get my pencil on, right? But when I differentiated the y, since it's the dependent variable, I didn't just call it the derivative of y as 1. It's y prime. It's dy dx. Now, once I get to this point, let me go ahead and solve for y prime. So I get 3y prime is equal to 12x. Last step is to solve, divide by 3, and I get y prime is equal to 12 divided by 3, that's 4x. 12x divided by 3. And notice, dig what I have there. These are the same. But in this situation, y was explicitly in terms of x, and here it was implicit. So this method that we're looking at here is called implicit differentiation. Now, let's explore this a little more. Let's suppose that we've got a circle. X squared plus y squared equals 1. Here's a nice unit circle. And let's suppose we want to look at the slope of tangents for the top part of this circle. Okay? So this is a circle, and I want to deal with the top part of the circle. Well, you know, one thing I could do is I could solve for y in this case. I could say, okay, y squared is equal to 1 minus x squared. And then take the square root. Since I'm dealing with the top part of the circle, I would just use the positive square root. Yeah. Now, I can differentiate this. No worries. Here we go. Here goes the derivative, dy dx. Now, there's going to be some chain rules involved. And by the way, or the chain rule involved, remember, this is 1 minus x squared to the 1/2. Okay, whenever I'm differentiating, I'm going to write it as a fractional exponent. So here we go. We've got the derivative of the outside times the derivative of the inside. See? And then we can cancel that, and what we get is our derivative is negative x over the square root of 1 minus x squared. See? You know, because this is a negative 1 minus x squared to the negative 1/2, so it's down here. Okay, there's dy dx. Now, let's go about this a different way. Let's proceed with what I'm calling implicit differentiation, where I'm not going to solve for y and get it explicitly in terms of x. So here I go. I'm going to go through here and differentiate everything I could get my little pencil on, right? So I've got 2x, okay, plus 2y, but when it comes to the y, I've got to remember to multiply by the derivative of the y. In other words, I've got to tack on a y prime. See, it's the chain rule. You differentiate the outside, that's the power rule, 2y times the derivative of the inside. Well, I don't know what y equals, so I'm just going to call it y prime. And then I've got the derivative of the other side, 1 is 0. Okay, so there is how you go through and perform this implicit differentiation. You differentiate everything you can get your hands on, but when you come to y, you tack on the y prime. Now I want to solve for y prime. So I've got 2y prime equals negative 2x, and I'm going to divide now by 2y. And I get this. I get that y prime is equal to negative x over y. Now, this is what y prime is. This is also over here what y prime is. You might think, well, these look different. But realize that y is equal to the square root of 1 minus x squared. So if I just replace this y with the square root of 1 minus x squared, these will look identical. See? So what I've done here is I have implicitly found a formula for the slope of tangents to the top part of this circle. It's implicit differentiation. And now, so now if I'm given a point, like for example, let's suppose I want to find the tangent. Let's suppose I want to find the tangent, the slope of the tangent. At a point, let's suppose at this point, square root of 3 over 2, comma 1/2. Let's suppose I want to find the slope of the tangent to this circle at that point. So I'm just dealing with the top part of this circle here. What I would do is I would say, okay, the slope, let me just say dy dx. Let me put a little line here, and I'm going to say at the square root of 3 over 2, 1/2. That's going to equal, here you go, square root of 3 over 2 up top, negative square root of 3 over 2 up top, and down in the bottom, 1/2. Yeah, that's it. So there you go. Now, if I multiply the top and the bottom by 2, I just get negative square root of 3. And there you have it. Okay, now, so let's go on and just look at a couple of these and practice this implicit differentiation. Let's suppose that we have a situation like this. Let's suppose that we have something like, x squared y cubed plus y to the 5th equals, let's say x cubed. Okay? And so here we've got something that might be a little more challenging to solve for y and then differentiate. So we're just going to go through here and use implicit differentiation. So what we want to do is we want to find dy dx. We want to find y prime. So here's what I'm going to do. I'm going to go through here on a differentiation rampage, just differentiating everything I can get my hands on. So I come to this term first. Now this is a product, so I'm going to have to use the product rule. So this is going to be 2x y cubed, okay, derivative of the first times the second, plus the derivative of the second times the first. Notice the derivative of the y cubed is 3y squared times y prime. Whenever I differentiate the y part, I've got to tack on the y prime times x squared. Okay, plus 5y to the fourth y prime. Got to tack on that y prime equals 3x squared. Yeah. Now, I've done my differentiation, but what I need to do is I need to solve for y prime. And whenever you do this, you're going to have a situation where you have y prime is going to be something that you can solve. Okay? We can solve for y prime. So here's the way we do it. We gather our y prime terms on the same side, move everything else to the other. So here's what we have. We have 3y squared x squared y prime. That's this first term right here. 3y squared x squared y prime. And we also have this one. We have 5y to the fourth y prime. And then on the other side, we have 3x squared, see that? Minus 2x y cubed. See, I just subtracted this from both sides, moved it over. Now, you might think, well, now what? Well, we can factor out a y prime from both of these. So now I have y prime, 3y squared, x squared, plus 5y to the fourth. Okay, equals 3x squared minus 2xy cubed. Yeah, that's it. Now, we're almost done. I need to divide by this. So I get y prime is equal to 3x squared minus 2xy cubed over this thing. Okay, plus 5y to the fourth. There we go. And that is our dy dx. Okay, let's try this bad boy. Now, so I'm going to go through term by term and differentiate. Now, this first one is a product. So let me start here. Derivative of the first, well, that's 4 times the second. Okay, there's the first. Plus the derivative of the second times the first. So here I go. I've got 3 times 4, okay, x, y squared, y prime. Okay, so look what I did. For the derivative of the second times the first, I've got 3 times 4, diminish the y by 1, just using the power rule and tacked on the y prime. And then there was the 4x, see, so 3 times 4 is 12. I kind of combined some steps there, but anyway, this right here is the derivative of this. Then I subtract off, I've got another product rule here. Now you have to watch your bad self here because there's a negative in front of this product. So you have to be very careful because it's easy to make a mistake here. And when I come to a situation like this, what I do is I just say, okay, I'm going to enclose this whole product rule work that I do here inside a bracket or parentheses. That way I don't mess up on my negatives, my signs. So here I go. Inside this, I'm going to say, okay, derivative of the first, 2xy, plus derivative of the second is just y prime. And I close that off. See, derivative of the first times second plus derivative of the second times the first, and the negatives in front there. Whew, good. So I don't really have to worry now because I'll know when I drop this parentheses to distribute the negative through. Now I have the x cubed. That's just going to be 3x squared minus Derivative of 5x is minus 5. Derivative of 6 is 0. And then, of course, there's a 0 over here. Okay, so there we have it. We've went through there and we've differentiated. We've gone on our differentiation rampage. Now, I need to solve for y prime, and that's going to involve clearing this parentheses right here, moving everything that's not y prime to the other side. So let's see what we've got now. We've got 4y cubed plus, I'm just going to do this a step at a time, okay, minus 2xy minus x squared y prime. Yeah, there we go. Okay, now I'm going to start separating things out. So if it's not got a y prime, it's going to go to the other side. So let's see what we have here. I'm keeping the y primes over here. So I've got 12xy squared y prime. There, got that one. That one's going to move. Here's minus x squared y prime. And that's it. Now I'm going to move everything else to the other side. Okay, so here I go. I've got the, I like a positive to be up front, so I'm going to move the 5 over first. 5, okay. And then I've got plus 2xy. Minus 3x squared. Minus 4y squared. 4y cubed. There. Okay, so I've moved all that over. Now I need to factor out a y prime. Okay, so here I go. I've got 12xy squared minus x squared y prime. Equals all of this over here. And then I just divide and I'm done. Okay, so here I go. I've got 5 plus 2xy minus 3x squared minus 4y cubed. Let's see here. And then divide it by all this business here. There. There's our derivative right there. Okay, now, so there's a couple of examples of how we use implicit differentiation. Now, with implicit differentiation, you can also find the second derivative. So, for example, let's just look at this. Let's go back to this problem we looked at earlier. We've got x squared plus y squared equals 1. And what I want to do now is I want to find the second derivative. So I want to find y double prime. So here I go. I'm going to go through here and differentiate. I've got 2x plus 2y y prime equals 0. And recall, let's just jump to the end. Recall that we had y prime is equal to negative x over y. So I just jumped to the end there. Now what I want to do is I want to find y double prime. Okay? So here I go. I'm going to differentiate. I'm just going to start here and differentiate through. So here I go. I've got y double prime. See, if I differentiate y prime, I get y double prime equals, now over here, I'm going to use the quotient rule. So here I go. I've got the derivative of the top, which is negative 1, times the bottom, okay, minus the derivative of the bottom times the top. And in this case, I just carried my negative along with the x. Okay. Okay, now let's see what we've got here. We've got negative y plus xy prime over y squared. Okay, now, so this is y double prime here, but we don't want to stop there. What we want to do is, we notice we've got a y prime here, and we would like for this whole thing just to be in terms of x and y. So what I want to do, in place of this y prime, I'm going to put the negative x over y. Okay, so here I go. I've got y double prime is equal to negative y plus x, negative x over y. Yeah, like that. See, I just replaced the y prime with negative x over y. And now, let's see what we've got here. We've got y double prime equals, now I don't like this, this fraction within a fraction up here, so I'm going to clear out this y by multiplying through by y, here, here, and here. So what I get is, I get negative y squared minus x squared, because the y's cancel, and down here, y cubed. See? I just multiplied everything by y. Here, here, and here. And the whole purpose was to get rid of that extra y denominator. Now, okay, so there it is. There's our second derivative. Now, we might want to notice something slick here. Notice that the original problem was x squared plus y squared equals 1. And look what we've got here. We've got negative y squared minus x squared. Well, what if I do this? What if I factor out the negative? This would be x squared plus y squared. And that looks like that's going to be negative 1 over y squared, y cubed. So, that's a cooler way to write it. So we've got y double prime equals negative 1 over y cubed. So there you have it. There's a way that you can find the second derivative using implicit differentiation.